I love space, but I'm sure you already know that because I made a iceberg of space mysteries a month ago. But I wanted even more, so we are back with more space mysteries, more disturbing things from space. Let me know what you guys want to see next in the comments, and be sure to leave a like, subscribe, Discord, Instagram in the description. Let's get into this, starting with the Great Attractor. The story of the Great Attractor starts with something that shouldn't have been happening. When astronomers mapped the motion of galaxies in our part of the universe, they expected them to be drifting apart in every direction thanks to cosmic expansion. Instead, they found something else layered on top of that expansion. A huge, coordinated bulk flow. Entire clusters of galaxies, including our own Milky Way, weren't just coasting outward, they were all drifting the same way, like a slow current in space dragging everything toward a single region in the constellations Centaurus and Norma. That invisible pull became known as the Great Attractor. And the creepy part is, whatever's doing the pulling is mostly hidden behind the Milky Way, blocked by dust and gas in what astronomers literally call the zone of avoidance. Astronomers first noticed the effect in the late 20th century while measuring peculiar velocities, the extra motion galaxies have on top of the normal expansion of the universe. The numbers didn't make sense. Our entire local group, the Milky Way, Andromeda, and dozens of smaller galaxies, is moving at over 600 kilometers per second toward that same patch of sky. You can even see the evidence in the cosmic microwave background. There's a temperature dipole in the CMB, one side slightly hotter and one slightly colder. And that's because we are literally moving towards something massive enough to warp the background radiation of the universe itself. When scientists tried to figure out what was there, they ran into a problem. Most of the region is blocked from view in visible light. It wasn't until infrared, radio, and X-ray surveys cut through the obstruction that a clearer picture emerged. Right at the heart of the pull is the Norma cluster, also called Able 3627, which is a monster galaxy cluster about 220 million light-years away. It's one of the most massive structures in the nearby universe, so dense and bright in X-rays that once the data was finally collected, it became so obvious that it was a key part of whatever is tugging on us. But even that wasn't the whole story. The more astronomers mapped the region, the more they realized the Great Attractor isn't a single object. It's a whole gravitational landscape, a chain of galaxy clusters, filaments, and walls of matter all sitting in one massive basin. In 2014, scientists finally reframed the entire problem by redefining what a supercluster actually is. Instead of just drawing boundaries around groups of galaxies, they mapped where everything is flowing. The result was Laniakea, a supercluster 500 million light-years wide, containing around 100,000 galaxies, including the Milky Way. And at the center of that gravitational basin, like the drain at the bottom of a cosmic sink, is the region that we have been calling the Great Attractor. Everything in Laniakea isn't just nearby in space, it's moving it downhill in the same gravitational direction. In other words, we're not just floating in the universe, we're sliding. And here's the part that makes it even darker. The Great Attractor might not even be the real endpoint. When researchers extended the map further out, they found an even bigger mass concentration beyond it. The Shapley supercluster, hundreds of millions of light-years past Norma, and possibly responsible for a large share of the pull we feel. So, the thing dragging our entire galaxy through space may not even be the final source of gravity. It might just be the closest ripple in a chain of even larger structures pulling on us from deeper in the cosmic web. So the Great Attractor isn't a single star or a black hole or something you can point to with a telescope. It's a direction. It's a gravitational current that we're caught in, pulling our whole galactic neighborhood towards something we still can't fully see and definitely can't escape. The universe isn't static, it's flowing, and we're part of that flow, whether we like it or not. Next, I want to talk about holographic theory. Most people hear holographic theory and they think that it means that reality is fake, like we're living in a cosmic 3D projection. But that's not actually what the theory says. The real holographic theory principle came from a much weirder place: black holes. See, in the 1970s, physicists Jacob Bekenstein and Stephen Hawking were trying to answer one question: what happens to information when something falls into a black hole? If a black hole destroys information, that breaks the laws of physics. But if it doesn't, then the information has to be stored somewhere. And that's when they notice something strange. The amount of information a black hole can contain, its entropy, doesn't scale with its volume. It scales with the surface area of its event horizon. In other words, the information inside a 3D object is somehow encoded on its 2D boundary. That one discovery shattered the way physics thought about space. Normally, if you have a box, you assume the amount of stuff you can fit inside depends on the box's volume, length times width times height. But black holes don't follow that rule. Their maximum information content is measured in square meters, not cubic meters. That's like saying everything in your room, every atom, every particle, every detail, could be fully described on the walls of the room, not inside it. Suddenly, the idea that reality is volumetric started to look more like an assumption instead of a law. By the 1990s, physicists Gerald T. Hooft and later Leonard Susskind pushed the idea even further. Maybe the entire universe works this way. Maybe the 3D world we experience is actually a kind of hologram. Not illusion, but encoding. Just like a regular hologram stores a 3D image on a 2D film, maybe the universe stores its information on some lower dimensional boundary. That's the real meaning of the holographic principle. Not that the world is fake, but that the true data of the universe might exist on a surface we can't directly see, and everything inside is the projection of that data into 3D. The wild part is that this isn't philosophy anymore. In 1997, physicist Juan Maltasenia gave the idea its first concrete mathematical form with something called ADS/CFT duality, a model where a universe with gravity in 3D space is exactly equivalent to a universe without gravity on a 2D boundary. Two different realities, same physics, same information. One has gravity and space inside it, the other is like a flat sheet of code. And both are valid descriptions of the same universe. Okay, so let me get a little bit more into this so it makes more sense. So the name ADS-CFT sounds kind of complicated, but the idea behind it is actually pretty bold. So on one side, there's a bulk universe, a full 3D world with gravity, curved space, and all the things that we take for granted. On the other side, there's a 2D boundary universe with no gravity at all, just quantum fields interacting on a flat surface like a sheet of code. And yet, mathematically, every particle, every force, every event in the 3D world has an exact counterpart on the 2D boundary. They're not similar theories, they are literally the same theory written in two different languages. And that's where the hologram analogy stops being metaphorical. In Maltasena's model, the 3D world emerges from the boundary, the same way a 3D hologram emerges when light hits a 2D film. If you know the boundary theory perfectly, you don't need to simulate the 3D universe, it's already encoded. This immediately changes the hierarchy of what's real. If the same universe can be described from inside it or from its boundary, then gravity and spacetime look less like fundamental ingredients and more like side effects, things that turn on once enough quantum information is arranged in the right pattern. That's why some physicists say spacetime is not the stage, it's the performance. The universe isn't built from atoms downward, it's built from information upward. And here's where it gets even stranger. When physicists started studying the holographic model more deeply, they realized that entanglement, the spooky quantum link that Einstein hated, might literally be the glue that holds space together. If two regions of the boundary lose entanglement, The corresponding regions in that bulk universe physically drift apart or break. Increased entanglement and space becomes more connected. In other words, the geometry of the universe, distances, curvature, even the existence of a smooth 3D world, may be nothing more than a side effect of how much information is shared between quantum systems. Think about what that implies. Space isn't a container, it's a relationship. The universe doesn't have coordinates built in. Coordinates only appear when information forms a consistent network. If that network changed or fragmented, the structure of space itself would dissolve. Not as an explosion, but like a computer program losing data. And that loops back to the original black hole puzzle. If information can't be destroyed, then nothing that falls into a black hole is truly gone. In a holographic universe, the lost information isn't inside the black hole at all. It's still on the boundary, scrambled, but preserved. What looks like a 3D object being swallowed is just the bulk picture. The true information never left the surface. This is the part that makes physicists uncomfortable because it flips the instinctive picture of reality. If the holographic principle is correct, then the deepest layer of the universe isn't made of particles or fields or even space-time. It's made of bits. Not computer bits, but physical ones. Yes/no. Something versus nothing. Distinguishable states of information. And everything else, mass, energy, distance, gravity, is what those bits look like when they're organized at astronomical scale. So when people say maybe the universe is a hologram, they're not saying it's fake, they're saying the 3D world might not be the master copy. The real version of the universe might be stored on a surface we can't access directly, a cosmic boundary where the laws of the universe are simpler, sharper, and fully accounted for. What we call reality might just be the high-resolution projection version. And here's the twist that no one mentions in pop science. If this is true, the boundary doesn't have to be physical. It could be a mathematical surface, or a horizon, or a limit of observation, like the edge of the universe we'll never see past. The boundary might not be out there, it might be a mathematical constant. It might be everywhere and nowhere, the way a hologram film is just plastic until light hits it. And that's where the theory stands today. Not proven, but not fringe either. So it's fucking interesting, but it's not like a proven thing or a real theory, you know? Next, I want to talk about the Firewall Paradox. So for decades, physicists thought that they finally understood black holes well enough to live with the weirdness. General relativity said that if you fell into one, nothing dramatic would happen at the event horizon. No explosion, no sudden force, no cosmic tripwire, just smooth normal space-time until you got deep enough inside for gravity to rip you apart. That idea is called the equivalence principle, and it basically says falling past the event horizon should feel the same as floating in empty space. In other words, black holes were supposed to be violent on the outside but calm on the threshold. Then, Hawking radiation changed everything. In the 1970s, Stephen Hawking discovered that black holes aren't actually black. They slowly leak radiation. And if they leak radiation, that means they evaporate over time. Which raises the question nobody could escape. If a black hole eventually disappears, what happens to the information about everything that fell in? Quantum mechanics says information can't be destroyed, ever, but relativity seemed to say that black holes swallow it permanently. That was the original information paradox, and for almost 40 years, people assumed the resolution would be subtle but harmless, something mathematical, not physical. By the 2000s, most physicists were leaning toward the holographic answer that we just talked about. That solved the information problem, but it quietly created a new one that nobody noticed until 2012. That year, 4 physicists, and here we go, me trying to pronounce these names, Al-Mahiri, Morozov, Polchinski, and Sully published a paper that detonated the calm consensus. They showed that if black holes really preserve information, and if Hawking radiation obeys normal quantum rules, then the smooth, harmless event horizon can't exist. The math doesn't allow for it. Instead, the horizon has to be a wall of high-energy radiation, a firewall that incinerates anything the moment it touches the edge of the black hole. And that's where the paradox lands. You can't have all 3 of the things physics wants to keep. You can't have, number 1, information being preserved, number 2, Hawking radiation being normal quantum radiation, And number 3, a smooth event horizon with no drama. One of those has to be wrong. If you save quantum mechanics, you kill Einstein's equivalence principle, and the horizon becomes a literal death wall. If you save reality and keep the horizon smooth, you have to let black holes destroy information, which breaks quantum physics. And if you try and save both, you're forced into something even stranger. Space-time itself has to stop being a local continuous thing. The simplest fix is the one almost no physicist wants to accept. Let black holes destroy information. That solves everything instantly. No firewalls, no paradox, no drama. But it comes at the cost of quantum mechanics, which is the most accurate theory humans have ever built. If information can be erased, then the basic logic of particles, atoms, and reality itself collapses. So almost nobody in modern physics is willing to pay that price. The second option is the one the Firewall paper is famous for. Keep quantum mechanics, keep unitarity, but accept that the event horizon isn't smooth. Instead of gliding in peacefully, anything falling toward the black hole slams into a wall of violent, high-energy radiation at the edge. No inside, no crossing, just instant death by quantum wildfire. This preserves information perfectly, because nothing really enters the black hole, but it breaks Einstein's equivalence principle, one of the core rules of relativity, and says space-time itself tears at the horizon. The third option is the strangest one, but it's the one most physicists are now drifting toward. Maybe space-time itself isn't fundamental. Maybe the inside and outside of a black hole aren't actually separate places. Maybe the Hawking radiation and the interior are really the same quantum system described in two different ways. This is where ideas like black hole complementarity, quantum extremal islands, and ER equals EPR come in. And that's just the theory that entanglement and wormholes are the same thing, and that the interior of a black hole is built out of the quantum information already outside it. In that picture, there is no firewall, not because the horizon isn't safe, but because the inside doesn't exist the way that we think it does. The space-time behind the horizon is a hologram of entanglement, not a physical region you can enter. That's the current frontier, not choosing between fire or smoothness, but questioning whether inside and outside are even meaningful concepts once quantum information is involved. The paradox didn't just break black holes, it cracked open the idea that space-time is a real, continuous fabric. In the new picture, space is something that emerges from quantum information. And when that information is arranged differently, space itself can disappear, overlap, or fold into something new. So the real legacy of the firewall problem isn't the fire, it's the realization that black holes aren't places, they're processes. They don't store information inside, they are information, arranged in a way that makes spacetime look like it exists. And if the universe works that way everywhere, not just at black holes, then the holographic principle isn't a curiosity, it's the operating system of reality. Next, I'm going to talk about the arrow of time. The arrow of time is one of those ideas that sounds simple, but quietly cuts right to the heart of what reality even means. In physics, almost every major law works perfectly in both directions. Newton's equations, relativity, quantum mechanics, they don't care if time runs forward or backward, but we do. We remember the past, not the future. We grow older, not younger. Heat flows from hot to cold. And one more example, glass shatters, but never unshatters. And the question is why? What gives time its direction when the math doesn't? The best answer we have comes from entropy, which is the measure of disorder. In the 19th century, Ludwig Boltzmann realized that the second law of thermodynamics isn't just about energy, it's about probability. Systems naturally move from unlikely ordered states to more likely disoriented states. That statistical drift is what we experience as time moving forward. A broken cup can't reassemble itself because there are billions more ways for the pieces to stay scattered than for them to snap perfectly back together. The universe doesn't prefer disorder, it just explores every possibility, and disordered ones overwhelmingly outnumber the tidy ones. Entropy increases, and that increase becomes the arrow of time. Cosmologists think the arrow began with the Big Bang, when the universe somehow started in a state of absurdly low entropy. That's the real mystery. Not why entropy grows, but why it ever had room to grow in the first place. The early universe was hot, dense, and almost perfectly uniform, conditions that, gravitationally speaking, are extremely ordered. As the cosmos expanded, it gained more space for matter to clump, stars to form, and entropy to rise. So our experience of time flowing forward may ultimately trace back to that improbable beginning. We're living in the long unwind of a cosmic setup that started way too neatly. There are other arrows layered on top of the thermodynamic one: psychological, cosmological, quantum, but they all seem to point the same way because they piggyback on entropy. Our memories form in the direction of increasing disorder. Cause precedes effect because the world keeps accumulating information in that direction. In theory, if the universe ever reached maximum entropy, total thermal equilibrium, the arrow of time would vanish. Nothing new would happen because before and after would stop meaning anything. So the flow of time isn't a fundamental law, it's an emergent illusion that comes from statistics and initial conditions. From the fact that the universe began in a rare wound-up state and has been relaxing ever since. Time feels like it's pulling us forward, but really we're just falling down the steepest gradient of probability the universe has ever known. Next, I'm gonna talk about rogue planets. When you think of a planet, you probably imagine it orbiting a star, basking in its light, tracing a regular path. But there's a class of worlds that defy that picture entirely. Planets drifting through space without a parent star. These are called rogue planets or free-floating planets. The idea of a planet without a star raises two fundamental questions. How did it get there, and what is it like now? On the formation side, there are two main possibilities. One, it formed in a planetary system like ours, but got violently ejected. During the chaotic early days of planetary systems, gravitational interactions between giant planets, stars, or passing objects can fling a planet out into interstellar space. And then the other main possibility is that it formed on its own, without ever being bound to a star. Some of the observed free-floating planetary mass objects may form by the collapse of gas clouds, in a way more like stars than planets. As for how common they are, that's where things get wild. Surveys that use gravitational microlensing, where a massive object passes between us and a giant star bending light, suggest that rogue planets might outnumber the stars in our Milky Way by large factors. One estimate from NASA suggests that there could be 20 times more rogue planets than stars, meaning trillions of them in our galaxy. Another study found hints of one free-floating world for every 4 stars in a certain mass range. Detecting them is extremely challenging because they don't glow like stars, they don't have a sun to reflect light, and they drift alone. Astronomers rely on methods like infrared surveys, trying to catch the faint heat of young or massive ones, and microlensing, which again is catching the brief signature of their gravity passing in front of another star. In recent years, the James Webb Space Telescope found several large free-floating worlds in the Perseus molecular cloud region that appear to have masses 5 to 10 times that of Jupiter and are not orbiting any star. Now let's talk about what these rogue planets mean and why they set off an uncanny feeling. Imagine a world drifting through space with no sun, no daylight, maybe no heat from a star. If it has internal heat left over from formation, or tidal heating if it has moons, it might hang on to some warmth, but generally, these planets are dark, cold, and isolated. Yet, in the deep galaxy, isolation is the norm for them. The sheer number of these rogue worlds suggests that planet formation is messy. Many worlds never find a stable orbit. Many planetary systems may spit out their smaller, unlucky members. This flips our view of planets like Earth from normal to maybe fortunate. There's also a bit of existential creepiness. If there are trillions of these dark wanderers drifting through the galaxy unnoticed, then the idea of planets bound to a star becomes a special case. These forgotten worlds could pass through interstellar space untouched and unseen for eons. They might intersect a stellar neighborhood, be captured by a star, or eventually drift into oblivion. One day, one of them could even pass through our solar system. Extremely unlikely, but not impossible. The vastness of space means the probability is tiny, but the number of rogue planets means the scenario exists. Now, finally, why does this matter scientifically? Several reasons. First, rogue planets provide a laboratory for understanding planet formation and migration, how systems evolve, how many worlds are cast out, and how many survive. Second, they test our ideas of habitability. Could a rogue planet with a thick atmosphere, internal heat, and maybe a subsurface ocean host life even without a star? Some scientists think yes, though the conditions would be extreme. And finally, third, they challenge detection technology and push us toward new methods, like microlensing surveys, that might uncover a whole hidden population of planets in our galaxy. Okay, next I'm going to talk about universe is inside a black hole. There's a theory that our entire universe, everything we see, every galaxy, every atom, even time itself, might exist inside a black hole. Not next to one, not orbiting one, but literally within the interior of a black hole that formed in another universe. It sounds absurd at first, but the idea actually comes out of trying to answer a really simple question. What happens to the stuff that falls into a black hole? According to general relativity, anything that crosses the event horizon keeps falling forever toward the center, where it gets crushed to infinite density in what's called a singularity. But physicists hate infinities. They usually mean your math has broken down, not that nature actually behaves that way. So some researchers started to ask, what if that singularity isn't a point of destruction, but a bridge? What if the matter and energy falling into a black hole don't vanish, but instead bounce or tunnel through to form a new expanding region of space-time on the other side? That's where this universe inside a black hole idea comes from. In this model, the Big Bang wasn't an explosion in empty space. It was the moment when a black hole in some parent universe gave birth to a new, expanding space-time bubble. From the outside, it would look just like another black hole. From the inside, to anyone living there, it would look like an entire universe that began in a burst of expansion. Exactly what we see when we look at our own cosmic history. In other words, the inside of a black hole could feel like a Big Bang to whatever forms within it. There are reasons that this actually makes sense mathematically. The equations that describe the inside of a black hole, the so-called Schwarzschild or Kerr solutions, can be extended to regions that look like expanding universes. The idea of a white hole, the time-reversed version of a black hole, naturally fits that description too. Some models, like the black hole cosmology proposed by Nikodym Popławski and others, suggest that the extreme compression near the core could cause a kind of quantum bounce, flipping collapse into expansion. That expansion would be sealed off from the parent universe by the event horizon, meaning that the new universe would be casually disconnected, self-contained, and effectively invisible from the outside. That's exactly what our universe looks like from the inside. It's also a neat solution to the black hole information paradox. If black holes spawn universes, then maybe the information about what fell in isn't destroyed, it's just encoded into the initial conditions of the next universe. Our universe could carry the quantum fingerprints of whatever existed before it. In that sense, every black hole might be a kind of cosmic seed, a generator of new universes with slightly different physical constants depending on the conditions of their birth. Of course, this is still theoretical. There's no way to peek beyond an event horizon and no clear way to tell whether our Big Bang was born from one. But it does explain a few coincidences that have always bothered cosmologists. The density of our universe, for example, is eerily close to the critical value that separates eternal expansion from eventual collapse. Exactly what you'd expect if it formed from the balance of forces at a black hole's horizon. And the shape of space-time we live in, finite yet unbounded, fits that same geometry perfectly. If this idea is right, then black holes aren't cosmic dead ends, they're the wombs of creation. Every time one forms, the singularity inside might explode into its own space and time, a completely new universe sealed off from ours. That would make our own Big Bang not the first, but just one link in an infinite chain of universes, each born from the death of another. And maybe one day, the black holes in our universe will give birth to others, a cycle of creation repeating forever in the dark. And that's the end of this video, guys. I hope you enjoyed learning some more disturbing things from space. I loved making this video. I hope you all have a great night. Thank you for watching, and sweet dreams.